All right, so on Monday, we went ahead and we color coded our periodic table. So you guys should not have any of the writing on here. You should just have your color codes and your colors shaded in, as well as the circles on your 1As, your 3A, 4A, all the way through 8A. The first thing that I want you to do is I want you to write down the letter N and denote that N is an energy level. And then we're going to write down 1 through 7 next to hydrogen through francium. We're going to do the same thing over on our right side of the periodic table. Write the letter N, 1 through 7. 7 is going to line up with UUQ. After you've done that, we're going to outline these dark stairs in just a dark color. Doesn't matter which one. And I want you to point at this row, the row that has helium through radon. This is known as our noble gases, so I want you to denote that those are there. That's going to be important for later on. Next, I want us to label letter D. So we've got our D orbital. D has an energy level of -1. So even though it's in row 4, -1 would make it 3. So we're going to have energy level 3 in front of scandium, energy level 4 in front of Y, energy level 5 in front of Lu, and energy level 6 in front of Lr. Our F orbital is N-2, or energy level -2. Remember, our F orbital is actually positioned in this spot right here. So in front of La, it's going to be 6-2, or 4. And in front of AC, it's going to be 7-2, or 5. So go ahead and pause this video and make sure that your periodic table looks like mine. You've got the same things written down. And then go ahead and get your note sheet because we're going to start our notes. Electron configuration. Your learning targets are as follows, so please go ahead and write these learning targets down in the W section of your KWL. Go ahead and pause the video if you need to fill these in. All right. First, we're going to talk about what orbital energies are in the atomic structure. So energy of an atomic orbital increases as the principal quantum number increases. Basically, energy increases as we move up the 2s, the 2p, 3s, and 3d orbitals. We also can note that 3d is higher in energy than the 4s orbital, and overlaps like this are going to occur very often, and you'll see that in the next chart.
Have you been using these?
So we'll see these overlaps in this next chart. So as you see in this chart, if we're trying to follow along in this, the energy level is going to increase as we go up this chart. So 1s is going to have a smaller energy than 2s. 2s is going to have a greater energy than, 2p is going to have a greater energy than 2s. 3s greater than 2p. 3p greater than 3s. 4s greater than 3p. 3d is greater than 4s. So as you can see, the energy level increases and our subshell electron capacity also increases as we go across. The s orbital can only fit 2 electrons. The p orbital can fit 6. The d can fit 10, and the f can fit 14. Electron configuration. The definition of electron configuration is going to be the arrangement of electrons in the orbitals of an atom. We explain this with a symbol that contains 3 pieces of information. The first piece of information is the principal quantum shell, or the energy level, which is denoted by the letter, a number, or the N that's on your periodic table. There also is going to be a letter for the orbital type, like the S, P, D, or F orbital. And lastly, there's going to be a superscript with a number, and this is going to be the number of electrons in a particular subshell. So for example, if we have 2p4, we're going to literally read that as 2p4. This indicates that there's 4 electrons in the p subshell of the second energy level. So energy level 2, because that's what is out in front, the p subshell, and there's 4 electrons in that p subshell. As you can see, there's another example down here. 1s1 indicates there's 1 electron in the s subshell of the first energy level. There's a few different principles and rules that are going to help with electron configuration. The first is the off-bow principle. The off-bow principle follows the idea that electrons are added to orbitals as protons are added to an atom, and each added electron is going to occupy the lowest energy that's available to it. So the main idea of the off-bow principle is that we're going to fill our lower energy subshells before we fill our higher energy subshells. So 1s is going to be filled before 2s or 2p. So if you follow this along, this Aufbau principle chart is actually going to be extremely helpful for you when filling out your electrons for elements. So we're going to start always with 1s. After 1s has been filled, we hit 2s. After 2s has been filled, we hit 2p, 3s. After that's been filled, 3p, 4s. Then we get to 3d, 4p, and 5s, and so forth. I'd put a star next to this. This is going to be something that's going to help you out quite a bit when we do some electron configuration practice. We also have this table here. Another thing I would star in your notes. This is going to be one of your best friends for helping you figure out how to do electron configuration. This shows you the energy level and the letter of the subshell where different elements exist at. So as you can see, hydrogen's in 1s, so is helium. If I were to ask about sulfur, sulfur exists at energy level 3p. So we'd have to get through 1s, 2s, 2p, 3s in order to get to sulfur and 3p. Orbital diagrams are a visual representation of electron configuration. Basically, they show the individual orbitals and pairing of the electrons within these orbitals. So if you look at helium, we've got 1s1. Sorry, hydrogen's 1s1, helium's 1s2, lithium is 1s2, 2s1. I'm going to pull up my camera and show you guys how we're finding these numbers. All right, so if we look at our periodic table, and we're going to try to go to lithium because I feel like that's an easy example to give to us. So we're going to try to figure out the electron configuration of lithium. So I'm going to draw, I'm going to put a little arrow on this sticky note so we can see exactly where we're trying to get. And I'm going to show you guys how we get there. So lithium is right here. Okay, so we're going to try to get to lithium. So lithium, in order to get to lithium, we're going to read this like a book. So we're going to read left to right out of our periodic table, and we're always going to start with hydrogen. To get to lithium, I have to read through hydrogen. So we're going to go through 1s, and there's 2 things that fit into 1s. Our s orbital always fits 2. Our p orbital can fit 6. Our d can fit 10, and our f can fit 14. So if we completely read through a level, just know that these are the numbers that you can write in. So we're completely reading through our level 1 to get down here to level 2 or 2s1. So we're going to fill 1s2 completely. Once we've finished this line, we come back down. Lithium is in spot 1 into the 2s orbital. So our code for lithium is 2s1. This is our electron configuration for lithium. Okay. Orbital diagrams are squares for each pair of electrons. So S's get 1 square. If we were to draw a orbital diagram for P, we'd have 3 squares. Okay. D would have 5 squares, and F would have 14 squares. So we'll get back into that here in a minute. In regards to orbital diagrams, we have what's known as Hund's rule. And Hund's rule is that every orbital in a sub-level is occupied by 1 electron before any orbital in it is occupied by 2. So we fill in the singles first. All of the electrons in a singly occupied orbital have to have the same spin or the same direction of their arrow. So we're going to fill in our upward arrows first, and we'll fill in our downward arrows second. So I'm going to go back to my periodic table, and I want yours out as well to help you figure this one out. So we're going to look at carbon. So carbon is what we're looking at on our periodic table. So I'm going to go ahead and move my sticky note over to carbon. As you can see here, our endpoint for carbon is in energy level 2. It's in the p suborbital, and it's 1, 2. So we're going to end at 2p2. All right, in order to get to carbon, I'm going to go through 1s before I get there. So carbon has 6 electrons. So I'm going to show you guys how there's 2 ways to do this. We can account for our electrons. So first we're going to fill 1s, and we're going to put 2 electrons in 1s. Or if we read through, we're putting 2 electrons in that way. Come down to 2. We need to get through lithium and beryllium in order to get over to carbon. So 2s is also filled. So 2s2. So this accounts for 4 electrons. So 2 plus 2 equals 4. So far we have 4 electrons accounted for, but carbon has 6 in total. So that means that there's going to be 2 electrons left in the p level, 2p2, and that is exactly where we're at. We're in spot 2 of the second energy level in the p subshell. So this is our configuration of carbon. We've accounted for all 6 electrons. 2 plus 2 plus 2 gives us 6. So all electrons are accounted for. I knew I had 6 electrons because if you look at carbon on your periodic table, it's atomic number 6. If we were to draw an electron diagram or an orbital diagram for this one, what we're going to do is we're going to have a square for our S, a square for our other S. P is going to have 3 squares. Okay. We're going to, our S is completely filled. So because our S is completely filled, we can go ahead and draw an up arrow and a down arrow. Our next S is also completely filled with 2 electrons, so an up arrow and a down arrow. Each of these boxes can only hold 2. So that's why for P, we need 3 boxes because 3 times 2 equals 6. We end at 2p2, so there's only 2 arrows that are going to go into our P boxes. So we're going to draw one up arrow and another up arrow. Hund's rule says that we cannot, the incorrect way would be to do this. So this is incorrect. This is not right. So instead we want to fill them in singly before we can fill them in doubly. All right? Go ahead and minimize this. So that's Hund's rule. The Pauli exclusion principle. Electrons must spin in opposite directions in each suborbital. This refers to the fact that certain particles cannot be at the same place at the same time with the same energy. I know that got caught out, but it says same time, same energy here. So we cannot have 2 up arrows. Instead, we need to always have one going one direction and one going another direction. Electron configuration helps us to understand what are known as valence electrons. Valence electrons are electrons that are occupied in the outermost shell or the highest energy level or highest value of N. We're going to say it's always going to be our highest energy level or the highest value of N. So those occupying an inner shell orbitals are called core electrons. So as you can see for sodium, we're going to go ahead and do the electron configuration together right now, and then we're going to come back to this and I'll show you the difference between the core and the valence electrons. So let me pull up my camera again, and we're going to go ahead and zoom in, and we're going to look at sodium. All right, so sodium's right here. I'm going to put my pen on it. And sodium has 11 electrons in total. So there's 2 different ways we can go about writing our electron configuration for sodium. We can read through our periodic table like a book, or we can just add up our electrons, and we know that our order is always going to be 1s, 2s, 2p, 3s, 3p, 4s, 3d, back to 4p. Okay, so let's go ahead and look at sodium. Sodium is number 11, so we know it has 11 electrons. In order to get to sodium, I'm going to read through 1s2. So I'm going to go ahead and write 1s2 down. I have 9 electrons I still need to account for. We also need to get through 2s2 in order to get down here to sodium. So we can write 2s2 down. 2 plus 2 is 4, so we still have 7 electrons to account for. In order to get to sodium, I have to completely read through 2p. So I'm going to go through all of these. 1, 2, 3, 4, 5, 6. So as you remember from earlier, the p orbital can fit 6 electrons. So if we completely fill up, or if we completely go through a p subshell, we can just know that that means 6. So 2p6. At this point in time, we've accounted for 10 electrons. We have 1 electron left to account for, and that is going to be where sodium's at. It's in level 3, it's in S subshell, and it's in spot 1. 1 plus 6 plus 2 plus 2 gives us 11 electrons, so we double checked. We've got our right number of electrons. Our ending point, 3, we're in the S subshell, and we're in spot 1, so that looks good. So this is our electron configuration for sodium. If I was to ask you to draw our orbital diagrams, we'd have a square for S, a square for this S, 3 squares for P, and one last square for that S. If we go ahead and fill this in, we're going to have an up arrow and a down arrow, an up arrow and a down arrow, up, 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 down, down, down. So all 6 are filled in, and 1 up for our sodium. Okay. Our highest value of N. So remember, it goes N, letter, and then number. N is our energy level. So our highest energy level for sodium is 3. So these guys are considered our core electrons, and this is considered our valence electron because our valence electrons are in our highest energy level. So Na has 1 valence electron. We're going to take some time and some practice together and go through how to configure electrons. In your packet that I gave to you guys, there's tons of practice problems. So we're going to go ahead and do a good chunk of these together to see if you can hopefully get the hang of configuring electrons. All right. So the first one that we have is P, phosphorus. Okay. I've made a orbital diagram chart for you down here that you can fill in as we go along. But let's look at phosphorus. All right, first we're going to find phosphorus on our periodic table. All right, phosphorus is right here. Okay. P, phosphorus. It's number 15, so it has 15 electrons. As you can see, we're going to have to get through 1s, 2s, 2p, 3s, 3p in order to get to phosphorus. So let's go ahead and kind of write this out. So to get to phosphorus, I know I need to get through 1s. 2 fit into 1s, so we're going to go ahead and write that down. 1s2. We also, to get to phosphorus, have to get through 2s. So we're going to go ahead and write down 2s2. So far, this has accounted for 4 of our 15 electrons. After 2s2, I'm going to go ahead and I have to get through 2p. And remember, 6 fit into the p orbital. So we're going to go ahead and write down 2p6. After the p orbital, we're back to 3. We're going to get through 3s2. So we have 8 plus 4, 12 electrons were accounted for. We need 3 more. If you look at phosphorus, we're in level 3. We're in the p orbital. It's in spot 3. So it's in 1, 2, 3. So our final part of our configuration is 3p3. Okay. Drawing our orbital diagrams for this one. We always fill our up arrows first. And we're going to go ahead and kind of edit our charts. So P, remember, gets 3 boxes. Okay. So P gets 3 boxes. So we want to make sure that those boxes are drawn in there. S obviously only gets 1 box. So S, we're going to have 2 electrons in our 1s, 2 electrons in our 2s. Our 2p is going to have 1, 2, 3, 4, 5, 6. Our 3s is going to have 2 electrons, and our 3p is going to have 3 electrons. Remember, we fill our up arrows first. So up arrows first, 1, 2, 3. If you count all of your lines, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We have our 15 electrons in total, or you could do 3 plus 2 plus 6, which equals 11, plus 4 gives us 15. Okay. So this is our configuration for phosphorus. Okay. Another way that we could look at this, or another way you could figure this out, phosphorus was in 3p. It was in spot 3p, 3. So you could write down, we know we've got to fill S, so 1s2, 2s2, 2p6, 3s2, and then we were in 3p3. So that's another way to do this. And another double way to check this, phosphorus is in level 3p. In order to get there, we have to get through 1s, 2s, 2p, 3s, and then we end at 3p3. Okay. All right, let's look at a few other examples. Next, we've got fluorine. Fluorine. So finding fluorine on our periodic table. All right. Fluorine is right here. Fluorine is number 9. Okay. So fluorine has 9 electrons. Fluorine is in 2p. So I know I'm going to get to 2p, and it's in spot 1, 2, 3, 4, 5. So our ending spot for fluorine is going to end up being 2p5. There's a few different ways we could do this. We could read through it like we did our last time. Another way of doing it is using our flow chart. So we know it's going to, if we're at 2p, this is our ending point, we know that we're going to fill 1s. So 2 fit into 1s, so I can go ahead and write down 1s2. We're trying to eventually get all the way to 2p5. So going back to that flow chart, after I filled 1s, I then fill 2s. So we're going to write 2s2. 4 of our electrons are accounted for so far. Once 2s is filled, we're going to fill 2p. Remember, we said we were ending at 2p5, so that's all we're going to write down, 2p5. 5 plus 2 is 7. 7 plus 2 is 9. So we've got our 9 electrons accounted for. In terms of our orbital diagrams, we need to fill in our p's. 1s2 is going to get 2 electrons. 2s2 is going to get 2 electrons. 2p5, we're going to fill our up arrows first. So that accounts for 3. And then we're going to go down, down, and now we have our 5. We have one unshared pair of electrons, or one electron in here that does not have a partner. All the rest are partnered up. We're going to do one more example for today, and then we'll do more examples tomorrow in class, okay? Argon, Ar. So we're going to find argon, Ar. Argon is over here, and its end spot is 3p6. 3p6. I want you to go ahead, pause the video, and see if you can figure out the configuration, the total configuration for argon. So go ahead and pause the video, and then we'll kind of check it together. Okay. Argon is going to end at 3p6, and we know it has 18 electrons. So 18 electrons is going to end at 3p6. So that's going to help us with some notes for this. All right, in order to get to 3p6, I have to get through 1s. So we're going to write down 1s2. In order to get to 3p6, I also have to go through 2s. So we're going to write down 2s2. We also have to get through 2p6. So we're going to write down 2p6. Remember, argon's all the way over here. We're down at level 3. We still have to get through 3s2. And then lastly, we're going to end on 3p6. If I added all of these up, 6 plus 2 is 8. 8 plus 6 is 14. 14 plus 2 is 16. And 16 plus 2 is 18. So we have our 18 electrons accounted for. We ended at 3p6, exactly like where our element was located. The last thing we have to do is we have to do our orbital diagrams. So remember, the p gets 2 extra lines because there's 3 boxes in the p. So 1s is going to get our up and down arrow. 2s is going to get an up and down arrow. 2p is going to get our 3 up arrows and then 3 down arrows to fill that p. S is going to get an up and a down, and the next P is going to get 1, 2, 3, 4, 5, 6. We always fill our up arrows first and our down arrows second. Okay. We're going to learn about how we incorporate the D and the F orbitals more in class tomorrow, and then we're going to have some time to practice together. So go ahead, do your best on seeing if you could try to figure out FE by using this flow chart to see if you could figure out FE as your homework for tonight. FE is right here. Make sure that you write it in pencil or maybe even on a scrap sheet of paper because we're going to come in and check it together in class on Thursday. I will post an exit slip for you guys to go ahead and try your best to answer. And besides that, you can use the rest of the hour to work on test corrections. Hope you guys have a great day, and I'll see you on Thursday.